Thank you everybody for joining today. Okay, so these are the things that we're going to be looking at today. I've got three sections here. I've got a short introductory section about the basics really, about how we can apply the property graph primitives, nodes, relationships, properties and labels in order to develop your own application graph data model. Okay. Then we're going to talk very briefly about how we can identify some of those elements. How can we identify a node versus how can we identify a relationship? How can we identify these things from your description of your domain? Okay. And then I'm going to address a couple of questions that typically come up, particularly around when do I use a property on a node versus when do I use a relationship, a node and a separate relationship in order to model an interesting or complex attribute value. Okay, so that's the basics, that's the first part of the webinar. In the middle, this is the bulk of the talk, we're going to look at some common graph structures. So the goal here is for you to develop your own application graph data model, a graph data model that's specific to your application, that models your domain and is available to be queried by something like Cypher in order to satisfy end-user functionality. Okay. So your application graph data model is going to be very specific to your domain. But nonetheless, there are a few graph structures that tend to crop up over and over again. And if you can identify opportunities for using or reusing these graph structures, your modeling efforts will be a lot easier. So I've picked three examples here. There's a number of different common graph structures, but the three that I'm looking at today are intermediate nodes, the use of intermediate nodes, the use of linked lists, and finally how to model versioned graphs, or how to introduce versioned structures into your application graph model. And then at the end of the webinar, we're going to look a little bit at how we can go about evolving a graph model. So you can develop your application graph model, you may end up building an application that you put into production, everything goes swimmingly. Nonetheless, things tend to change, requirements change, you learn more about your domain, there are other kinds of queries that you want to execute, or you want to optimize your model for specific queries. At some point or other, you are going to have to change your graph data model. How can we go about that? Okay, so let's just talk very briefly about some of the basics of data modeling. Okay. As I say, with Neo4j, you have 4 graph primitives that are available for you to model your own application model. Nodes, relationships, properties, and labels. And the questions we're answering here really are, when do I use a node? When do I use a relationship? What do I use them for? So nodes. Okay. I tend to use nodes to model entities, things in your domain that have identity. There might be physical things, people, products. There might be concepts or expressions or calculations. Anything in your domain that has identity will tend to model that as a node. And each individual instance of a thing will model as a separate node. Okay? So here in my very, very simple diagram, I've got 3 nodes, one of which represents a person, and 2 of which represent skills. Now we can attach properties to each of those nodes, key value pairs. We can attach 1 or more properties to each node, and no 2 nodes need to share exactly the same set of properties. But we'll use the properties to represent entity attributes. So you can see for the node at the top here, we have a username property representing that person's username. And for the skills, we've got name properties here, the names of the skills. So we tend to use properties on nodes to represent entity attributes. And we can also use them occasionally to capture some metadata as well, perhaps a version number or some timestamps. So entity attributes plus metadata, that's when we use properties on a node. So at this point, we just have little islands of information, discrete records representing the things that we're interested in. We then connect these records, or we connect these entities using relationships. So every relationship in Neo4j has a name and a direction. And the name and the direction together help lend semantic context. We understand what these nodes mean, partly as a function of the ways in which they're connected, the ways in which they're related or connected to other things around them. So we use the relationships to connect the nodes, and we use the relationships to introduce structure into the graph. So instead of having little discrete islands of information, we're now beginning to structure all that information using these relationships. And the wonderful thing is we're doing this at the level of the individual instances, the individual entity instances, the individual nodes. So no two nodes need to be connected in exactly the same way. Even if we've got multiple user nodes within our system, no two user nodes need to be connected to other things within our domain in exactly the same way. There's no uniformity, it's not necessarily uniform. And this is why I often say that graphs are a wonderful way of modeling variably structured data. Domains where the connections between things vary or change as we navigate that domain's landscape. Okay. So we're using the relationships here to connect entities. And as with nodes, we can attach properties to those relationships. But whereas with nodes, we use properties to represent entity attributes, with relationships, we'll tend to attach a property in order to represent the strength or the weight or the quality of that relationship. So the relationship already has a name, that's intrinsic to the relationship, but we can further qualify the relationship by adding one or more properties that help specify the strength or the weight or the quality. So we might specify the strength of a relationship. Here in my model, I've got a couple of relationships, a couple of has-skill relationships, there's the name, but I've attached a level property indicating Ian's proficiency with regard to these two skills. So he's level 3, whatever that may mean in our domain. He's level 3 with regard to Neo4j, but he's level 2 with regard to REST. Okay. We also might use properties, in a transport network to represent the time it takes for a train to move between two stations, or the length of a road. And using these numeric values, we can very easily apply a shortest weighted path algorithm, for example, across the graph. Okay. So we're using properties to represent the strength or the weight or the quality. And again, we can also use them to attach some metadata to the relationships. And actually later on in the talk, we'll see some examples where I'm using them to attach some metadata to the relationships in order to version the graph. So metadata such as version numbers or timestamps. And then the last primitive that we have available to us are labels. Okay, so you can see in my little sample here, I've labeled each of the nodes. Now we tend to use labels to represent the role that a node plays within our domain. So we attach labels to nodes. We can attach more than one label to a node. We can actually attach 2 labels to this node at the top, saying that Ian is both a person and a user within our system, or an administrator, something like that. You might play several different roles within this domain. We don't have to attach a label to a node, but if we do, we can actually attach more than one. So we use labels to represent the role that a node plays within our domain. And this is very useful, once we've retrieved some data from Neo4j, perhaps we want to turn that data into some objects, or we want to display it on the screen. We need to understand what these specific nodes represent. Is this a person? Is it a product? And so on. And this is one of the functions of the labels here. The labels also give us the ability to group nodes. So we can ask the database, find me all of the nodes labeled person, or find me all of the nodes labeled skill. And as you're probably aware, the labels are also our hooks today into attaching indexing and some very lightweight constraints. So we can tell the database, look, I want you to index all of the nodes in my data set labeled person, and I want you to index them based on their username property. Okay. So that's one way in which we can use labels in order to provide very simple indexing. We can also use them to specify some constraints, a uniqueness constraint. I could say, look, every node in my database or in my graph that is labeled person, I want you to ensure that the username property is unique within the context of this data set. So this is a very quick rundown of the 4 primitives and the way typically we use them. Okay, so this is just general advice. This is the kind of happy path advice. There are always exceptions to the rule, but typically I use nodes to represent things. I then structure the relationships or the connections between those things using relationships, and I use labels to represent the roles that the nodes are playing within my domain. So how do I actually go about identifying these things in the first place? How do I identify an entity? How do I identify the ways in which things are connected? Well, the ordinary language that we use to talk about our domain can help surface these entities and these relationships. They can give us the candidate label names, the candidate relationship names. They can help us identify node instances. So, when we're talking about our domain, if we start using common nouns, things such as user or email, these are the things that become candidate label names. When I'm talking about all of the users within my system, it's likely that I'm probably going to want to represent each of those users as a node, and I want to indicate that node's playing the role of a user within my domain. So this common noun user becomes the label user. Email, Ian sent an email, or Ian sends a number of emails. We might have a number of nodes representing different emails, and we'll label each of those email. Similarly, verbs that take an object tend to become candidate relationship names. So Ian sent an email, or Ian wrote a review. You can imagine we've got nodes representing Ian, and other nodes representing his emails and his reviews, and we can connect them together using sent relationships and wrote relationships. And then finally, where we identify, or we're talking with using proper nouns, Ian, Jim, Bob, London, New York, typically we'll end up representing these things as nodes. These are entity instances. So we want to represent each of these things as its own individual unique node, and we'll use properties to capture the attributes of these entities. So here we'd end up creating a node that represents Ian, we'd attach a name property, and we'd probably end up attaching one of those labels, perhaps user, something like that. So we've got our primitives, and a very simple way of beginning to identify what's a node, what's a relationship, based on the way in which I talk about my domain. But given that background, people very quickly start to ask a number of interesting questions. Okay, I've identified my entities, I've identified some of the attributes of the things that I'm interested in. But I've got an interesting attribute here of this particular entity. Should I just represent it or model it as a property on my node, or should I pull that attribute out and actually model it as a separate node and connect it to its parent, as it were, using a separate relationship? When do I use properties, and when do I use relationships plus a separate node to represent an entity attribute? Now the answer here is, well, there's no one-size-fits-all answer. There's an art here. But it's about steering between two extremes, and the two extremes I've illustrated with this diagram here. Both of these are, I think, bad ways of modeling a domain using Neo4j's property model. At the top left, we've decided to break every single entity attribute out into its own separate node. So we're trying to model a person plus that person's home address and work address, but every single attribute, first name, last name, age, first line of an address, the postcode, the zip code, or whatever, we've pulled out as a separate node. This is kind of very atomic decomposition of the domain in order to be able to build our own graph model. Now, we can do this in Neo4j, but we're kind of neglecting some of the power that the labeled property graph model gives us. We're neglecting the fact that we can attach more than one property to a node. We can kind of chunk properties up and create a record-like structure that brings together a set of properties that help represent an attribute. So we're effectively neglecting the property part of the labeled property graph model here when we're building something such as the diagram at the top left. At the other extreme, this thing on the bottom right, we've created one giant godlike node to represent something that we're interested in. And we've tried to lever everything in, all the things that we know about this particular person, we've tried to lever into this one single node. So not only do we have a first name and a last name property and an age, but we've also tried to lever in these two addresses as well, the home address and the work address. Now, if you're familiar with the way in which we store and represent properties today in Neo4j, you'll know that things such as home address and work address, well, the way in which we'd likely have to store them is something like a string array. Okay, so we'd have a home address property, and then the value of that would be a string array. And we need some application logic, some logic in our application that knows that element 0 is the first line, the second element is the second line of the address, and so on. Right. This feels to me to be a very clumsy way of trying to model everything. Okay. And what we're neglecting here is the fact that we have lots of relationships to play with. Okay, we can actually pull out some of this interesting information, pull it out as a separate node, and connect it to the parent using a named and directed relationship. And that would actually structure the graph and give us lots of semantic context, actually enhance the semantics of the model that we're building. So the guidance that I have, or this is the kind of rule of thumb that I tend to apply, is use a relationship. I've got an entity attribute. Do I pull it out as a separate node and use a relationship? Yes, if one or more of these things applies. So use a relationship when there's something interesting about the way in which that attribute value is actually connected to the entity in question. If there's something interesting about the relationship itself, the connection itself. So if I need to specify the weight or the strength or the quality of the connection between the entity and its attribute value, then I most certainly want to pull it out as a separate node and use a relationship. So being able to qualify friendship strength, or being able to qualify my proficiency with regard to a particular skill. There's something about, I have a number of skills, Neo4j, Java, REST, and so on, but there's something interesting about the way in which I'm related to each of those skills. I'm qualitatively related to each of those skills. I'm an expert in some, and I'm a beginner in others. So I want to qualify the way in which those property values are attached to me. I'd almost certainly pull them out as a separate node, and then I can qualify the relationship. So that's one reason why I might consider doing it. The second reason is if the attribute value itself is a complex value type. That is, if in itself that attribute value has a number of different fields. An address is the great example here. An address has a first line, a second line, a zip code, and so on. So again, an address is something we'd likely pull out as a separate node, and then we can attach that to our parent using a named and directed relationship. The third reason is, well, perhaps those attribute values, they're actually connected to each other in some interesting way. The very simple graphs that we've been looking at so far show a person and some of the skills that person has. Well, it may be that those skills in themselves are part of a skills taxonomy, so they're related amongst themselves. There are connections between those skills. So again, we can pull them out and begin to build up a taxonomy of skills. So again, another good reason for pulling out those attribute values and modeling them as separate nodes. Other reasons that people tend to apply when they're thinking through these questions, if the attribute value can actually exist independently of its parent, then again, we probably model it as a separate node. An address is a good example again. More than one person can share an address, and that address can exist independently of any one individual. So it's not dependent upon the existence of a particular person. So we pull the address out, model it as a separate node. Okay. The last reason we might consider modeling even a simple attribute value as a separate node, if it's going to be the starting point for lots and lots of our queries. If we're going to write lots of Cypher queries that will begin with this particular attribute value and then explore large portions of the graph surrounding that attribute value, then again, there's a good case here for pulling it out as a separate node rather than just modeling it as an attribute value as a property on a node. Okay. So, this is just an expansion of the diagram we've been looking at earlier, but here I've actually chosen to model each skill within my domain as a separate node. I could, you can imagine an alternative model in which Ian and Lucy and Bill each have a skills property which comprises a string array, and for Ian that string array would have the values Java, C#, and Neo4j. But instead I've chosen to pull these things out, and again, applying those little rules of thumb, we can see that there's something interesting about the way in which each of these skills is related or connected to the people who possess those skills. So I've qualified each of those relationships with that level property. Similarly, a lot of the queries that I want to execute in this particular domain, we're not going to look at those queries during this webinar, but I think they crop up in that previous webinar that I mentioned. A lot of those queries begin with the skills themselves. So they're the starting point. Find me all of the people who have the skills Java and C# or Java and Neo4j. So we want to bind to those particular nodes and then explore the graph that's immediately attached to them. So again, another good reason for pulling these things out as separate nodes. The alternative, model your entity attribute as a property on the parent node, and both of these things have to obtain, both of these things have to be true, when there's no need to qualify the relationship. There's nothing interesting about the way in which this entity attribute or this attribute value is attached to the entity, and the attribute value is a simple value type, eye color, for example, or age. There aren't multiple fields for this attribute value, just a single value, as it were, and there's nothing interesting about the way in which this thing is attached to the entity. Therefore, just model it as a property on the node itself. Okay, so that's the basic rundown, the way in which we can apply those graph primitives in order to model some of the interesting stuff in our domain, the way in which we can identify candidate nodes, labels, and relationships just by looking at some of the language that we use to describe our domain, and then looking at the issue of when to model an entity attribute as a property and when to model it as a separate node and a relationship. The key here really is to use the relationships. You've got a graph data model, use it. The relationships are your royal road into the graph, the royal road that your queries can use in order to explore the graph and generate answers on behalf of your application. So don't be afraid to use relationships. Introduce lots of relationships. The key thing here is align the relationships that you create with your use cases. Tend to as we talked about earlier, using the natural language in your domain, the way in which you talk about your domain, will help surface those relationship names. Use those relationship names in your model. So having well-named relationships is key when it comes to querying the graph, because a good graph query seeks to exclude as much of the graph as quickly as possible. It wants to throw away or grey out large swathes of graph. And we can do that by ignoring relationship names that aren't immediately applicable to the query or the question that we're asking. So if we just choose a very, very generic relationship name, if everything is connected to everything else using the same relationship name, it's going to make it far more difficult for our queries, for our Cypher queries, to grey out or exclude large portions of the graph without having to interrogate something else, without having to interrogate a property value, make a decision about a property value, and so on. But if all we're doing is following very specifically named relationships, we will ignore all of the others. The other advantage to being able to aligning relationships with your use cases is that it effectively allows you to specialize the graph over and over again on behalf of particular queries. So what do I mean by this? Well, I mean that we can connect the same things, our entities, we can connect them over and over again in lots and lots of different ways to answer different questions. And if we use differently named relationships and we write some good queries that only take advantage of the relationships we're interested in for that particular query, we're effectively being able to apply lots of specialization and still get all of the benefits of the graph. Okay. So now we're going to look at some common graph structures. As I say, when you're developing your own application graph model, you're going to come up with something, a description of the domain that's very specific to you, and therefore labels and relationship names that are very specific to your application. Nonetheless, there are some structural elements that occur over and over again, and these are the kind of things that you should probably be taking advantage of in order to smooth your modeling effort. So the first thing here is what I call intermediate nodes. So here are several different common requirements. The first is that you want to connect more than two entities or more than two nodes in a single context. So imagine, here's a description. Ian bought this particular book in Waterstones. Okay, so we've got three different things here. We've got a node that represents Ian, we've got a node that represents a particular book that he's bought recently, and we've got a node representing the shop Waterstones. So we want to bring all of these three things together. We're describing a particular fact here, the fact that Ian bought the book. We want to bring all of these three things together in the context, in a single context to describe that fact. So that's one of the drivers for using intermediate nodes, and we'll look at what the intermediate node comprises in a second. Second driver here is what's often called in data modeling terms n-ary relationships. So Sue invited Sarah, Bob and Charlie to her party. You can imagine perhaps ideally what you would like to be able to do is to create a relationship that extends from Sue and somehow branches to connect to Sarah, Bob and Charlie. Okay. Well, we know that we can't do that in Neo4j. Every relationship in Neo4j has to have one start node and one end node. It can't have one start node and three different end nodes. But nonetheless, this kind of situation crops up very often. The third reason, this is a bit subtle here, but the third reason we often need to introduce an intermediate node is because somehow or another we want to further qualify a relationship. We want to attach something to a relationship itself. So, diagram at the bottom of the screen here, Patrick worked at Acme in the role of software developer. And somehow or another we're wanting to qualify this worked at relationship by describing the role that Patrick was playing when he worked at Acme. Now I've used dashed lines here to indicate that this kind of structure isn't possible in Neo4j. We can't attach a relationship to another relationship. But as you're thinking about your model, thinking about your domain, you often come up across situations where you imagine or you think it would be most appropriate to somehow or other be able to attach one relationship to another. Well, again, this is indicative that you should be using something like an intermediate node. And this is an intermediate node. It's the thing that sits in the middle here. It allows you to connect all of the things that you're interested in together. So here we can see that Patrick worked at Acme in the role of software developer, but we've introduced a node in the middle that allows me to connect all those different dimensions. So again, we've got a single context here, multiple things or multiple dimensions that we're interested in, and we're connecting them all by way of this middle or intermediate node. Now, the nice thing is that this intermediate node probably actually represents something of genuine interest within your domain. I mean, here, this node in the middle represents an instance of employment. It represents a job. Okay, so Patrick had the job with the role software developer at the company Acme. But now we've got that node, and we're attaching some additional properties to it. We're attaching some timestamp properties here to indicate how long that job or that instance of employment lasted. Similarly, if we want to talk about a specific party, here we had Sue invited Sarah, Bob and Charlie to her party and sent out a number of invitations, we can introduce an intermediate node and then have relationships extending outwards to all of the people that Sue invited to her party. So, intermediate nodes, sometimes they're very obvious, and sometimes you should start thinking about them when you reach a bit of a roadblock, when you reach a bit of a block with your modeling efforts. And The reason you might reach a block with your modeling efforts is because of this language habit that we have, which we call verbing. Okay. So I said that we can often derive candidate label names, candidate relationship names. We can often identify specific node instances just by looking at the language that we use to describe our domain. That's great. But on the other hand, we have to be very aware of some of the little linguistic tricks that we use every day in order to come up with very concise utterances. And one of these little linguistic tricks that we have is verbing, where we take a noun and we create a verb from it. So if I were being very, very explicit, I might say, Ian sent an email to Bob. But more often than not, we just say Ian emailed Bob. We've taken the noun here, email, there are such things as emails, and we've turned it into a verb, email. And when we just have a natural language description, Ian emailed Bob, we think, oh yeah, emailed, that's a relationship. Ian is directly connected to Bob by way of an emailed relationship. Similarly, we might say Ian searched Google. Well, Ian Googled for this, he Googled for that. The noun Google has actually become the verb to Google. Okay. So these are some of the little language traps that we fall into. And if we're trying to derive our domain just from the language that we use, if we're trying to derive our model from the language that we use to describe our domain, then we can often end up coming up with a model that's a little bit off and often hitting a bit of a roadblock. So here's the situation that I mentioned a moment ago. We've got Bill emailed Lucy, Bill emailed Ben. Everything looks fine here. It seems to make sense. We can look at this. We can very easily understand what was going on. But then we might want to ask, well, okay, Bill emailed Lucy, but did he copy anybody else into that email? Did he blind copy other people in? All right. How would we model that? Feels a bit difficult, feels a bit tricky. It's one of those situations where we're thinking, oh, what I probably want to do here is attach another relationship to my emailed relationship that pointed to the people that I'd CC'd. Okay. This is an immediate signal, this is a smell really, that something's missing in our model. Okay. And this really is the model that we're interested in. Okay. Bill sent an email to Lucy. And now that email comprises an intermediate node, and we can very easily attach other nodes representing the people to whom Bill CC'd or BCC'd that email. Okay. So there was a thing hidden away inside of the verb. There was the thing, email, hidden away inside the verb, emailed. And it didn't become immediately apparent until we perhaps pursued our modeling efforts a little, started trying to write some queries or introduce new functionality into our application, and suddenly we realize, oh, we also need to introduce or to capture the details of CCs and BCCs, and now our model's a little bit wrong. Okay, so this is often the kind of driver for introducing an intermediate node, when some other requirement emerges and you discover that you've introduced a relationship, whereas in fact you should probably have introduced a node in the middle here. And actually in the example towards the end, when I talk about evolving the graph model and refactoring the graph model, I'll show you how we can take the structure on the left and transform it into the structure on the right. So another thing to take away at this point is do as much as is necessary for your immediate requirements, but no more. Don't try and over-model your world. Don't try and identify, break it down into lots and lots of specific nodes that you're never going to need. Start with the simplest model that works for your immediate use cases, confident that you can evolve that model over time. And here we need to break out a separate email node from our emailed relationship. I know I can do that. I know I can refactor to that structure on the right, and I'll show you how we can do that a little later on. So, we can start simple and get more complex as and when we need, but no sooner, no earlier. So the key points here with regard to intermediate nodes, they provide a lot of flexibility. If you're supremely confident that you're modeling something as a relationship, you're actually modeling an entity as a relationship, but you're doing that for convenience, for performance. If you're supremely confident that this entity that you're modeling as a relationship, this is a very odd use of relationships, but if it can only ever be connected to two other things, everything's probably okay. But if you feel as though you're going to want to introduce other dimensions at some point in the future, far better from the outset to model this thing as an intermediate node. Remember, intermediate nodes allow more than two things to be connected in the same context, in a single context, to represent all the different dimensions of a fact, as it were. So our second common graph structure is linked lists. And I use linked lists all the time in the models that I build. And again, here are some of the drivers. It may be that naturally within your domain, the entities that you're interested in are linked in some kind of sequence. They're ordered in a particular sequence. It may be actually that they're ordered in several different sequences. Depending upon the perspective, depending upon the use case, these things are all linked to one another, but they're linked in a different order depending upon the use case. But nonetheless, the stuff that you're interested in is connected as part of a list, as part of an ordered list, and you want to be able to reconstruct that list very, very quickly. So you have a need to be able to traverse the sequence, to find a starting point, to find an end point, and to find all of the things in between within that particular ordering. It may be that you have the need to identify the start or the end of a list. What's the most recent thing that was added to the list, or what was the thing that was added earliest? What was the very first thing that was added to the list? So it may be that you want to effectively maintain pointers to the beginning and the end of a list. So examples here, event streams. You've got devices within your network, you've got user events in your web app, and you want to capture all of these things. Each event is an individual instance of a thing. It's likely a node. You want to capture all of these things as nodes, but you want to be able to reconstruct the sequence at some point in the future through your queries. So you'd likely use a linked list. Modeling all of the episodes in a TV series. Okay, which episode followed which, in the order of transmission. And the third example here, a person's job history. I worked at this company between 2000 and 2002. I worked at a second company for the next 3 years, and so on. And I want to be able to reconstruct that person's job history. Again, this is effectively a series of events. Okay. So here's a very, very simple linked list. These are all of the stories. Let me have a look. These are all the stories that comprise season 12 of Doctor Who, some way back in the 1970s. So the very first story that was broadcast was Robot. The very last story that was broadcast was Revenge of the Cybermen. So this is the sequence of stories in the order in which they were broadcast. Okay. And you see that I can navigate this linked list very, very easily from beginning to end, from start to end, by following the outgoing next relationships. I can also traverse the list in the opposite direction, simply by going the wrong way down a one-way street. I can write a Cypher query that looks for incoming next relationships and follows those. So I could start with Revenge of the Cybermen and work my way back in time, as it were, in order to find the reverse order in which these things were broadcast. Okay. So here I've structured these things on behalf of a particular use case, this use case being I need to be able to reconstruct all of the episodes in the order in which they were broadcast on TV. But perhaps there are some other use cases in my application that need the same things connected, but in an entirely different way. Okay. This is where it gets more interesting. This is where we can actually introduce interleaved linked lists. Okay. So the next relationships here still specify the order in which episodes or stories were broadcast on TV. But the next in production relationships actually show me the order in which the episodes were filmed, or the order in which the stories were filmed. So we can see that when the BBC came to record season 12 of Doctor Who, they started by recording Robot, but the next thing that they went on to record was the Sontaran experiment, then the Ark in Space, then Revenge of the Cybermen, and finally they recorded Genesis of the Daleks, even though Genesis of the Daleks wasn't the last thing to be broadcast. Okay. So this is an example of specializing by using different relationship names according to different use cases. Now I can reconstruct the order in which things were broadcast and the order in which they were produced. Okay? And as long as my queries are focused on one or other of those relationships, we'll ignore all of the others. Okay? I get the best of both worlds. I can also introduce pointers here. So I've got another node representing season 12 in its entirety, as it were. Perhaps there's some properties that I want to attach to my knowledge about season 12 in its entirety, but then I've got pointers to the first and the last. And in a query, all I'd need do is bind to that season 12 node, follow the outgoing first relationship, and then I can very quickly navigate that structure in order to reconstruct the order in which things were broadcast on TV. So linked lists, I think, one of the simplest, but one of the most powerful common graph structures that you can use. The third thing that I'm going to talk about here, the third kind of common graph structure or third common requirement that people often have, is around versioning graphs. So the goal here is that you want to be able to reconstruct the state and the structure of the graph at a particular point in time. Okay. So you've built an application, lots of things happen in your application in response to end user events, and in the course of that your graph is changing over time. You're creating new users, creating new products, modifying the structure of the graph, modifying the prices of products and so on, just as an example. But then you want to be able to say, well look, going back 6 months, which users did we have, what were the price of specific products and so on, what was the state of the graph at a particular point in time. So this for me is the requirement to version the graph and be able to recover different versions of that graph. Now the example that I'm doing here is time-based versioning. Okay, so being able to recover the state of the graph at a particular point in time. The nice thing about time-based versioning is that as long as we have one component in the system that's responsible for generating our timestamps, for understanding what particular time is it now, and so on, then we have a universal versioning scheme. Doesn't matter what entities we have in our domain, the mix of those entities, the entire composition of our domain, everything has a particular state at a particular point in time. It's a universal versioning scheme. It's very simply implemented. All we're going to do is to timestamp stuff with long values that represent milliseconds since the epoch. Okay, so it's the same underlying mechanism that you see in lots of date-time implementations on different platforms. Now the key to versioning a graph is being able to separate structure from state. This is the key insight here. In order to be able to version a graph, we need to be able to separate graph structure from the state of specific entities. Okay. Now we'll see some examples in a moment. What you'll notice immediately is that the graph structure, the overall graph, does look a lot more complex. It's not as easily read as some of the examples that we've seen previously. Nonetheless, it provides this power of being able to recover the state of the graph at a particular point in time. So we want to separate structure from state. So on the one hand, I just want to be able to model the overall structure of my graph. And remember, going back to the beginning of the webinar, we introduce structure into a graph using relationships. The relationships are all about structuring the graph, connecting those individual records, connecting those little islands of information. So we want to be able to version the structure, version those relationships. And if any of those relationships change, if we introduce new relationships or remove relationships, or if the strength or the weight or quality of a particular relationship changes, this to me is all about the structure changing, then we need to be able to capture that information in our model. So what we're going to create are what I call structural relationships in the graph, and we're going to anchor those relationships using simple identity nodes. The identity nodes are placeholders for the real entities that are at the end of those relationships. This will make a bit more sense once we see an example. Okay, so the nodes at the end of these structural relationships are pretty empty. They probably just have a synthetic ID, and that's all. The other thing that we do is that we timestamp all of the relationships here. We attach a to and a from property to every relationship, effectively saying this particular relationship and its values, if we've got some other properties attached to that relationship, this relationship and its values are valid for this particular period of time. And if any of those values change, or if we delete the relationship, then we will effectively model that by modifying the to and the from timestamp properties, effectively saying the state of this relationship was valid for this particular period in time. Okay. And then, so that's just modeling the pure structure within the graph. But then also, obviously, we have all of the entities, the things that we're really interested in our domain. So we're going to model those as separate nodes. And in fact, we're going to model the state of those entities as separate nodes. So every time the state of an entity changes, we're going to create a new node. So every node is a snapshot of the state of an entity at a particular point in time. And then we connect these state nodes, these snapshots of state, back into our version structure using what I call timestamp state relationships. So we've got identity relationships and state relationships. Here, finally, is a diagram that hopefully makes this a bit more explicit. Okay, so the blue represents the pure structure. Okay, so remember, structure is all about the relationships. So you can see that we've got shops that sell products, and the products are supplied by particular suppliers. And this overall structure of our domain is represented by the relationships in blue. And the nodes in blue are those identity nodes, those placeholders that just allow us to reconstruct the state of the domain at a particular point in time. Okay. So these relationships here in blue, the names of these relationships are very much the kind of names of relationships that you would normally create when you were creating an unversioned graph structure. So Ian sent an email, Ian bought a book. These are exactly the kind of names that we would use here when we're modeling the structure of our versioned graph. And then everything in red represents the state of particular entities at particular points in time. So if we look towards the top, we've got a node, a blue node, shop ID 2, that's a kind of placeholder node. But then we've got a red state relationship that extends from that to a red node that represents the state of that shop at a particular point in time. Okay, so the name of that shop was Corner Shop, it's a little corner shop, and it's valid from the 1st of January until, well, there's no upper bound. Effectively, I've got a magic number here, this is max long, to represent the fact that this is almost an open time period that extends from the 1st of January 2014, and we haven't effectively closed that time period off at this particular point in time. So the really long numbers beginning 9, 2, 2, 3, that's max long, okay, infinity as it were. It's a magic number that says, well, this particular relationship, the timestamp here, the from value hasn't been closed off at this point in time. So you can see we've got a shop, sells a particular product. That product in turn has a node representing a snapshot of the state of that product at a particular point in time. So all of the state nodes, the nodes that represent the snapshots of state, are connected to their identity nodes using a state relationship. So whereas all the blue relationships, the relationship names come from our domain, we've got sells and supplied by and so on. In order to connect all of the snapshots of state into this structure, we're using a state relationship, which is effectively, it's not part of our domain, it's part of our strategy for creating a versioned graph. Okay. Yeah, so this is just Hopefully you can see all those details on your screen, but I've just blown one up here to show you that we've got a placeholder node, the product placeholder node, connected to a snapshot of the state of that product at a particular point in time, using a state relationship, a timestamp state relationship. Okay. So what happens? Over time, things occur and we begin to modify our graph. Perhaps in this particular example, one shop stops selling a particular product and another shop starts selling it. So this is the situation that we've captured here. We've started introducing some additional relationships here. So again, I've blown this up a little bit. But we can see that shop 1, at some point in the past, used to sell product 1. Okay? And in our earlier version of the diagram, you can see, when we first set this up, when we captured our first snapshot of our domain, you can see that indeed shop 1 used to sell product 1, and that sales relationship had no upper bound. It was valid from the 1st of January through to we don't know when. But at some point in time, in fact on the 1st of February 2014, shop 1 stopped selling product 1, and coincidentally perhaps shop 2 started selling it. So what we do here is we timestamp the old relationship with the current date time, and then we create a new relationship from shop 2 to product 1, and again we timestamp that sales relationship with the from value, the current date time, the 1st of February, and its to value, this magic number, this no upper bound, as it were. Okay. So now we can see that the dashed relationship here was applicable for a specific bounded period of time, and the new sales relationship was introduced on the 1st of February and is the current sales relationship in this particular instance. So this is how we would actually go about doing this in Cypher. This is how we would introduce this change to the structure of the graph. So we know that we're dealing with a particular shop, or we're dealing with a particular product. So we can create a match clause that identifies that product's, the node that represents the identity of that product. And you'll notice here that we're looking for the relationship that connects it to a shop where that relationship currently has no upper bound. So effectively what we're saying here with this match clause is find the current structural relationship that attaches this product ID node to the shop ID node. And then a little later on in the query, we're now closing off that period. So previously, the to from property values on that relationship were effectively saying this is the current relationship, it has no upper bound. But now we're closing it off. We're saying, look, on the 1st of February, this relationship stopped being valid. Okay? And then we can create a new structural relationship. We can match the new shop, and we can create a new sales relationship that extends from that second shop down to our product identity node. And again, we're creating timestamps that say this is valid from the 1st of February 2014, and it effectively has no upper bound. This is the current sales relationship here. So it's a very simple Cypher query. Well, it's not as simple as it would be if we weren't doing version graphs. Nonetheless, it's not too difficult. We identify the old structural relationship, or the set of structural relationships that we want to modify. We modify them, and then we introduce the new structural relationships. We can do all of that effectively within a single Cypher statement. So all of this will be done in the context of a single transaction. So when the transaction completes, we know that we will have modified the graph. Okay. The same thing occurs if the state of a particular entity changes. So with our previous example, we were modifying the structure of the graph. Shop 1 stopped selling the product and shop 2 started selling it. So this was a change in the structure of the graph. Here, what we're doing is actually changing the state of a particular entity. So product 1, on the 1st of February, again, coincidentally, 1st of February, but on the 1st of February, the price of this product changed from £1 to £2. So it's a very similar procedure. I'm not going to show you the cipher for this, but effectively we want to archive off that old state relationship and introduce a new one. So you can see here what I'm effectively creating here is a radial set of state nodes that extend from this product ID node. This is one way of tackling the problem. You can see I'm creating that radial set of state nodes. An alternative is to create a linked list that hangs off of that product ID node. And every time the state changes, we attach a new node to the end of that linked list. But I think, if I anticipate that each of these things within my domain is only going to change 100, a couple of thousand times, then I'm quite happy to have radial ID nodes with state nodes around them. A couple of thousand of these state relationships doesn't seem to me to be a particular issue. Okay, so that's all about modifying the graph, but then of course we want to be able to query the graph in order to be able to recover the state of the graph at a particular point in time. So imagine we want to write a query that says, find me all of the products sold by Shop 1 on the 5th of February 2014. So what was the state of the graph, or the state of the graph surrounding Shop 1 on the 5th of February 2014? So this is the query that will actually answer that question, and I'm just going to talk it through in bit by bit. So again, just noted at the bottom here that the 5th of February, when we turn that into milliseconds since the epoch, it's this large number beginning 13915. Okay. So in the first part of the query here, we're simply finding all of the structure that's attached to Shop 1 that is relevant for the point in time that we're interested in. So again, we're looking up Shop 1 based on that synthetic ID, and then we're finding all of the outgoing sales relationships that connect that shop to product identity nodes. And then the where clause here is helping restrict the relationships that we're actually really interested in. So you can see here in the blow up that at the top there I've got the ID nodes, the identity node that represents Shop 1. It's got two outgoing sales relationships. The one on the left, the dashed sales relationship, doesn't match that where clause. Okay, so that relationship's from timestamp is, let me see, I can't get these things straight in my head. Anyway, we know that that relationship is not valid, whereas the relationship on the right hand side is valid. Okay, so we're effectively identifying the structure of the graph that is valid for the 5th of February 2014. So that will lead us to another ID node or several ID nodes at the end of the relationships that are valid. So in the second part of the query here, having found the identity nodes at the end of those sales relationships that are valid, we can now begin to query them for the state of the products at that point in time, the snapshot of state. So again, we're doing something similar. We're interrogating all of the outgoing state relationships, the relationships in red, seeing whether they match, whether the timestamps fall within the period that we're interested in. And in this case, yes, there's one outgoing relationship and it's valid for the period in time that we're interested in. So now we can take the red node at the end there, which represents the snapshot of state for that product at that particular point in time, and we can create the return clause that generates a projection of that data on behalf of the client. Okay. So over the last year, I've had lots of people ask about being able to version graphs. This is one strategy for being able to do it. There are variations here. I mentioned one variation where instead of having radial state nodes, we might have a linked list. But the key insight is being able to separate structure from state and effectively being able to version these two things independently, even though they're part of the same graph. The benefits to the technique that I've adopted here is that on the whole it's purely additive. We don't ever actually delete nodes or delete relationships. We're just adding stuff. Okay. People have asked, well, why don't you add a from relationship only when you're closing off that time period? You know, Cypher gives us the ability to ask something, do you actually have a relationship? And do you actually have a property? If one of our time-stamped relationships doesn't have a from property, we could effectively say, well, that's the current relationship. Well, the reason I chose that magic number and introduced it, it ensured that all of those property values, the to and the from property values, they most likely get inlined in the same property record. So I know something about the store format on disk. I'm dropping down a level. I know something about the implementation of Neo4j. I know that those two property values, if they're created at exactly the same time, will be inlined in the same property record. This is going to be a more efficient storage mechanism on disk. Even though at some point I may want to change the value of that from relationship, I'll still be just changing its value inside of that property record. Whereas if I introduce a from property much later in time, it will be created in another property record, perhaps elsewhere on disk. Now, the downside of all of this, as is immediately obvious, is we end up creating a lot more data. Every time something changes, we end up creating new nodes and new relationships. You know, so there's an order of magnitude increase in the size of your graph and its size on disk. And as you can see, all of the queries that we write have to be time sensitive, or almost all of the queries that we write have to be time sensitive. So all of the queries, even the simplest query, becomes more complex because we're always having to introduce these where clauses that are comparing timestamps. And naturally, some of the queries are going to be a little slower because we're going to have to search slightly more of the graph in order to answer ostensibly the same question. So instead of just getting direct to a node that represents a product, we're going to have to bind to a product ID node and then navigate outwards in order to find the node that represents the state of that product. So we're already having to explore just a tiny bit more of the graph. So that's going to introduce a little bit more latency. And if you've got more complex queries or need to explore much larger swathes of graph, this is going to have an effect or an impact on the performance of those queries. So there are trade-offs here. We are being able to version the graph. We're doing it by creating an in-graph model that helps represent snapshots of state and changes in the structure of the graph, but it's making things more complex, it's introducing a lot more data, and it potentially has some impact on the performance of our queries. Okay. So we've looked at three common graph structures. We've looked at linked lists. Before that, we looked at intermediate nodes, and then we've looked at some of the common structures that we can use for being able to version portions of the graph. There are many others, but you know, they're three of the things that I think have been of particular interest to me over the last couple of years, and things that may be useful to you. So in the last part of today's webinar, we're going to talk very quickly about how we can then go about evolving our graph model. So as I said, we can start simple. We're building our graph model, we're aligning it with our use cases. You know, feature by feature, one piece of functionality after another, we modify our graph structure in order to satisfy those use cases. We're perhaps introducing new kinds of relationship, and so on. At some point, you build an application, you put it into production. At that point, things get a bit trickier to change. You know, whilst this thing's first in development, it's very easy to modify your graph model, to change things, swap them around. But the moment you have real commitments, the moment your system's in production, it's going to be far more difficult to change that model. Or if you are going to change it, you want to be able to do it in a reliable and robust manner. But things will change. You'll learn more about your domain. The business context might change. Or there are new feature requirements, new pieces of functionality that you need to introduce. Or you need to tune or specialize the model for specific performance reasons. So over and over again, there's always a requirement to be able to evolve your model. So we need some mechanism for refactoring a graph model. I've taken the definition of refactoring, of code refactoring, and I've modified it slightly to apply to what we might do with a graph model. So when we refactor the graph, effectively what we want to do is to restructure the graph without actually changing its information or semantics. So we still want to be able to discover the same kinds of information, but perhaps in a more effective manner, or we want to introduce new information, but we're going to do that by restructuring the graph in some manner. And the reasons for doing that I've mentioned already. Okay. So as part of a refactoring, what we're likely going to have to do is to actually modify the structure in place. We're going to have to migrate our data from one structure to another. Now, these are some of the things that you should bear in mind when you're doing that. The commands that we're going to issue against our data, we ought to be able to execute them in a repeatable order. Okay, so they ought to be a consistent order that we repeat over and over again, that we're confident can take structure A and modify it, transform it into structure B. But whenever we're doing this, make sure you back up your database. Okay, practice against other versions of your data. And if you're doing a lot of the test-driven data modeling, then actually you'll have a lot of confidence based on that you can refactor from one structure to another. As we'll see in the example that I've got here, all the refactorings that we perform today, we tend to do in a batch-oriented fashion. So the thing is, perhaps you've now got a very large graph, many millions of nodes, many millions of relationships, and there's something that you want to change that is actually going to impact many millions of nodes or relationships. The truth is, you're probably not going to be able to do that in one go, just by issuing one cipher statement and letting it chug away. The reason being, we're going to have to do all of this in the context of a transaction. And with Neo4j today, when we execute a transaction, we build up a lot of in-memory transactional state. And if we're building up a lot of in-memory transactional state for many millions of nodes and relationships, at some point or another, we're going to blow the heap. We're going to run out of memory. So it's likely what you're going to have to do is to create statements or commands that just modify portions of the graph bit by bit, and gradually we're going to migrate the whole thing over. So we want to create commands that we can repeat over and over again. So I've got a very specific example here that demonstrates how we do this. The problem here is I've modeled something as a relationship. Ian emailed Bill. I've modeled a thing as a relationship, and then I realize, oops, I made a mistake. Ideally, that relationship should be a separate node. It should be Ian sent an email to Bill. So I need to be able to extract a node from an existing relationship. Okay. So the solution here is we want to take all of those existing relationships in our graph, all of those emailed relationships in our graph, and for each relationship we want to create a new email node. We want to copy all of the properties that were originally on the relationship into the new node, because in this particular example, all of the emailed relationships also include the content of emails. We want to copy all of those properties over. We want to connect our new email node to the sender and the receiver, and then we want to delete the old relationship. Okay, so we want to take this structure, Bill emailed Lucy, Bill emailed Ben, and we want to modify it so that we end up with Bill sent an email to Lucy and another one to Ben. So the steps that we're going to go through, this is the general process. This is this doesn't apply just to this example. This is something you can repeat over and over again. Is to write a query that selects a batch of currently unmodified nodes and relationships. So it identifies a portion of your graph that hasn't currently been ported over to the new structure. We're then going to take the batch that you've identified, the nodes and the relationships that you've identified, and we're going to modify them. Okay? So that may be we create a new node, we introduce new relationships, and so on. Step 3, we perhaps need to do some cleanup. Perhaps we want to remove the old relationships, delete the old ones, so that we're just keeping the new structure. And then step 4, as part of this query, we're actually going to return the count of the number of elements that we've modified. Okay? And then we repeat steps 1 to 4 until this batch count drops to 0. So we're going to, the moment we can no longer find anything that needs changing in the graph, we're done. But until that point, we're going to continue executing this query over and over again. So this is the refactoring that we can perform to extract an email node from an email relationship and delete the old relationship. And I'll go through it. I'll go through those separate steps that we've talked about. The first one here is we're identifying some of the unmodified portions of the graph. We're finding all of those emailed relationships that connect one user to another. And you can see here that in the with clause, I'm effectively limiting the number of elements that I want to capture. I've given it a ridiculously low batch size here. In fact, in many examples, you can actually deal in the order of thousands or tens of thousands. And we can actually build up a lot of transactional state, but I've just given it a ridiculously low. So we're just going to identify two examples of this pattern. User A emailing some other user somewhere else. Okay, so we're going to take that subset of data and we're going to pipe it through to the rest of the query. So this is the unmodified portion of data that we want to use to create the new stuff. So in the next part of the query, we're actually creating the new structure. We're creating a new node to represent the email, and in creating that node, we're actually copying over all of the properties from the old one. So you can see here I've introduced a content property on my email node, and I'm setting the value of that content property to be the value of the content property on the old emailed relationship. So property values in the old part of the structure are now being copied over into the new. The merge statement here is then introducing the relationships between persons A and B and the email node. So we've got the sent relationship and the to relationship. This is that optional step 3. We don't want those old emailed relationships anymore, so we're going to delete them. And then finally, we're going to return a count of the number of relationships that we've identified and deleted. And we're going to continue to execute this statement over and over again until that number deleted value that's returned from the query reaches 0. Now, I was working with a colleague yesterday on something very, very similar to this, a graph with many millions of nodes and relationships. We had a pretty large upper limit size, and we were able to modify the whole thing in place in under a minute just by executing this thing a couple of times, setting a much larger limit than 2 here. That's effectively the technique that we can use. Okay, so that brings me to the end. We've looked at some of the very basics, how we can identify nodes, relationships, properties, and labels. We've looked at some common graph structures, and then we've looked at some of the techniques that we can use for modifying graphs as we're evolving our application over time.